All right, so hopefully this, if you've watched the last couple of videos for some reason, guys, with like 10 minutes to go to class, the audio just stops working. So I don't know what's going on with my headphones, but hopefully maybe this one has got it fixed. But this is number 9 from. This 11? Yeah. Okay. So there's 2 ways of doing this. And usually, guys, when I say there's 2 ways of doing something or 3 ways, that really means that there's 2 ways of kind of like organizing your work, but the technique is the same, or the procedure is the same. It's just 2 different ways of maybe expressing it. So the first one is to recognize that term right there, because of the parentheses, that is one object, right? Okay, 2x plus 5, just one object. Is that the same object? Yeah. Yeah. Okay. So what we're saying here is that we got an object cubed, and we've got an object to the 4th, and those are the same objects. So there's a GCF here. That object is the GCF. Let's factor that object out. If I take a 2x plus 5, okay, now how many times is that object inside each of these?
3.
Yeah, it's in there at least 3 times in each of them, right? So let's take a 2x plus 5 to the 3rd out. When I do that, if you factor this thing out, if you took 2x plus 5 out of this whole term 3 times, what would you be left with? You'd be left with 2x plus 5. If you factored it out 3 times out of this whole term, what would you be left with? -1. Good. Okay. Now remember, so when I'm factoring is just a fancy word for what operation? Division, right? Okay. So kind of think about what this is saying. And I think this is important to be able to make these connections, because a lot of times if you can make these types of connections and you forget a rule, or you forget what we're supposed to be allowed to do here, but you realize that 2x plus 5 to the 4th really just means that, right? Okay. Now I'm going to put brackets around that, and now I'm going to say I'm going to divide out 2x plus 5 to the 3rd. But if I divide out 2x plus 5 to the 3rd, isn't it just doing that? Okay, so this right here is this idea right here. Do 3 of those cancel with 3 of those, and leaves you with just that one right there. Does that make sense? Okay. And if I look at the second one, then the numerator really is just going to be so assume I am erasing that. It would just be 2x plus 5 times 2x plus 5 times 2x plus 5 over itself. Those cancel out and leaves you with just 1, right? Does that kind of make sense? So if we make those connections, it's going to make things a little bit easier for us to realize that this was correct. This is what we're looking for. I don't know why. Let's do it this way. Okay. So, at this stage here, you can rewrite this, obviously, as 2x plus 5 to the 3rd times, this is going to turn into 2x plus 4, doesn't it? Order of operations allows me to, order of operations and the associative property allows me to associate those two and combine like terms. So then I get 0. So then I have 2x plus 5 cubed is equal to 0, because I've got two factors now, right? Two factors multiplying together give me 0. One of them or both of them have to be 0. Now this one here actually has three factors kind of wrapped up inside it, but it's okay. I can do it this way. How do I get into this 2x plus 5? I need a cube root. So I have 2x plus 5. What's the cube root of 0? 0. So this is, it looks like we're just letting things go away, right? Just letting that root or that power disappear. But we are taking the cube root of both sides. You can take the cube root of 0, you just get 0. So then x will end up equaling negative 5 halves. Okay? Now, we'll come back and talk about this in a moment, but there is kind of a unique relationship here happening. I see this as a singular solution, right? Okay? It's not. It's actually a triple root. And we'll talk about that in a moment. Solve this one, I get x to be negative 2, right? Okay? Now the reason this is actually a triple root is come back up with what that means right there. 2x plus 5 to the third. Doesn't that mean 2x plus 5 times 2x plus 5 times 2x plus 5 equals 0? If we got three things equal to 0, can I say each one of those equals 0? So I would have 2x plus 5 equaling 0 3 different times. I could solve that 3 different times and still get x equals negative 5 halves 3 different times, right? So we get a multiplicity of 3 there, which we'll eventually talk about how that impacts our graph. But those are then the two solutions for that initial equation. If you were to graph that, you're going to see the curve pass through negative 5 halves, or negative 2.5, and negative 2.
Do you have to put it in 3 times as you go through?
No, you should. The only time that you'll have to put it in 3 times is when it'll be like chapter 4, and they'll actually say include like the multiplicity of the 0 or something like that. So if you just type in, so it should put like brackets for you. You're going to look at negative 5 halves, comma, negative 2. If you type it in that way, you should be good to go. Okay. Now, let's approach it a different way. Okay, and this is revisiting a little bit of what we did last week. The last question on Friday incorporated this, and it's called U substitution. Okay, this is a position where we can use that technique to make things a little bit clearer. Okay, what I'm going to do is I'm going to look at that 2x plus 5, and I see it there as well. And that's the thing that kind of maybe organizationally, if that's a word, confuses us when we're writing stuff down. I think it makes this line right here very messy if I'm going to leave it as 2x plus 5. So what I like to do is let u equal 2x plus 5. Let it be that object that is repeating itself throughout the problem. Okay? If I do that, does this turn into u to the 4th?
Yep.
Minus u to the 3rd equals 0? Does that make sense? Which that is the exact same thing as what we've got here to start with. But now what can I factor out of both of these? U to the 3rd, right?
Can you just subtract that?
Say again?
Can't you just subtract that?
I can make it just u?
Yeah, that's what I was thinking.
No. Because u times u times u times u minus u times u times u doesn't give me just u. Think about this. Let's say u is a 2. If I take 2 times 2 times 2 times 2 minus 2 times 2 times 2, does that difference give me what you're saying would be 2? Does that make sense? It does not, right? So this would give me what, 16 minus 8? Okay, 16 minus 8 does not give me 2, which would have been the u that we used here. So I can't just subtract those because of the powers. If they were coefficients, then yeah. Okay. So now when I do this, okay, this line right here is analogous to this one right here. And then if I want to go ahead and say u cubed is equal to 0 and u minus 1 is equal to 0. So u cubed obviously is 0, but u then is 1 here, right? Can I now, once I've solved for u, I'm going to back substitute. I'm going to replace u with what I let it be at the beginning. Actually, let's do it this way. Because it might make a little bit more sense for some of us. We could do it. We could substitute right there. But can I actually do this? Can I say u is equal to 0? Can I take the cube root right there and the cube root right there? What's the cube root of 0? 0. Okay. So I've got these two things, u equals 0 and u equals 1. Well, if u was 2x plus 5, does that give me x to be negative 5 halves again?
Yeah.
And if u was 2x plus 5, does it give me x to be negative 2 there?
Yeah.
That makes sense? Okay. Now, I probably wrote more things in blue over there than I needed to. I wrote u equals 1 several times there. But I think using u substitution is going to make less work. It's going to make your work more concise. It's going to make it look cleaner. And I think it's a little bit easier to keep track of, what did I factor out and what am I left with after I factor that out. So that's a technique there that is going to be very useful for you. The idea with u substitution, guys, is that you want to choose u strategically, meaning that I want to be able to replace many things with the same u. Does that make sense? Or many things with versions of u as I can. I don't want to say, let u be 5, and that only thing I can replace is the 5 up there, right? I still have x's, and that would be a problem. So now I've got two variables. So what you want to do when you're going to use u substitution, you're going to want to pick it creatively so that when you do substitute, you're left only with the variables u in your problem. Okay? A lot of things that we do, there's kind of structure and strategy to it that is kind of laid out in the problem, in the kind of the initial version of the problem. When you get to calculus, you will have to be kind of creative and make those decisions, maybe not necessarily knowing that it's going to kind of work out or pan out for you. So you might make a u substitution in calculus that doesn't get rid of all your variables, and you got to go back and say, okay, that didn't work. Let's try a different version of what we're substituting u with, okay, and see if that works. Does that make sense? Sometimes it's kind of a trial and error. But most things we do, there's going to be a pattern to it. For example, this one here. This is of quadratic form. This is very similar. That is the one we did last week, right? No, sorry. We did this one last week. Okay, we finished here on example 3 on Friday. Let's come down here to, it says equations in quadratic form. This is very similar to what we finished with on Friday. If we remember, quadratic form meant that they were a times your variable squared plus b times your variable to the first plus a constant was equal to 0. Okay? If that exponent is half of that one, okay? Sometimes you see this explained, if you ever see it written out in notes or something, maybe you'd see it written this way. If in M or in a 1 to 2 ratio. Okay. Now I said in, maybe I should say respectively. So the n goes with the 1 and m goes with the 2. So the m is twice as big as the n. Does that make sense, everybody? Okay, you might see it expressed that way because it doesn't have to be 1 and 2. It could be 2 and 4 like we see here. It could be 3 and 6. It could be 4 and 8. It could be 100 and 200. Does that make sense to everybody? Okay? If there's a 1 to 2 relationship, so that's what we're seeing here, then we're going to use U substitution. We're going to let U equal, now you only let it equal the variable component. You do not bring in the coefficient. There are situations where you can incorporate the variable, but they're far and few in between. That it's really just not a practice that we're even going to talk about very much. So we're going to let U be that, x squared. Okay? And then I'm going to just test to see that I've created the correct U. I've chosen the correct U. I should be able to square it. Now I'm only doing this because it's of quadratic, well I think it's of quadratic form. Okay? And if I square U, well U I just let be x squared, right? So squaring U would actually, in regards to being x's, would be that, right? What's x squared squared? X to the 4th. I like that because now, not only does this give me U and x squared, so I can replace x squared with U, right? It now gives me something I can replace x to the 4th with. I can replace x to the 4th with U squared. And that step right there kind of tells you why we would not take the coefficient with U and x squared. Okay? If the coefficient for x to the 4th was 16, then I'd probably take the 4 with x squared. Does that make sense? But I'm never going to take that. The safest thing, guys, is never take the coefficient. Okay? If that coefficient and that coefficient are, if this one is, if the 4 is the square root of this one, you can take it. Okay? But it's just, like I said, that's really rare that happens anyways. So now that we have this, now that we've defined our variables correctly, I'm going to replace. I'm going to do the substitution. So x to the 4th turns into what? U squared. Minus 4, x squared turns into what? U. And then plus 3 is equal to 0. I think that's a much easier process to think about what this thing is going to factor into by transforming it into a quadratic. Now you can factor this. What's U squared minus 4U plus 3 equals 0 factor 2? What are my two factors that multiply together? Give me 3. Good. Minus 3, minus 1. So that gives me U to be 3 and U to be 1, right? Now I solve for U. What was I trying to solve for? Trying to solve for X, ain't I? So let's this step here, you hear me call it back substitute. And that just basically says you introduced a variable U to make the procedure simpler. Once you solve for U, you're going to undo that substitution. You need to back substitute. So basically it means, well, U was actually x squared. So I've got x squared is really equal to 3. And x squared is really equal to 1. And that should generate very simple equations for you to continue solving. How do I solve for x here? Square root. Just remember when you introduce the square root, it's plus or minus. We get 4 solutions, and that matches up to the 4th power that we had in our original equation. Yes, please.
We were requesting extension. What happened?
I'll either give it to you or not give it to you. That assignment's going to get moved up anyways. something that I've seen, guys, is, and I understand the urge here, because how valuable your time is to you, that when we're going over questions, you've got WebAssign open, that's fine. But as we're going, I see people working on problems, and inevitably, two things are going to happen. You're going to miss something that we talk about in here, and you're going to, at some point, look back and say, oh, I need to ask that question, but it's already been answered in class, but you missed it. Or you're multitasking, and you're not going to be trying to listen to me on a different problem while working on your individual problem just to get the answer, and that's not helping you. Does that make sense? Okay. I understand that desire to get it done so you don't have homework tonight, but the idea of us going over them in class like this is so that you can learn the knowledge, so that when you do get home tonight, you can at least minimize the amount of time you have to spend on it. Does that make sense? Okay. If we continue to, as Mr. Fay is going over the questions, work on our individual problems, I will close off the assignments. They'll open up one day and be due the next day. Okay, and that will multiply the amount of work that you got to do at home. Does that make sense? Okay. So refrain. If it means close your computer, then that's what it means. I'm not making that a requirement, but I think that's important for us to understand. Over the last 5 or 6 years, people doing this are usually people that struggle. They're trying to multitask. They mess their problems up because they use one of their numbers and then accidentally use one of my numbers, and they get confused. And it just creates a bigger gap in their understanding than what they initially had. Okay? Let's do this one. Okay, so this is another one that is of quadratic form. Yes?
For use substitution, is it always you or can it be?
So they use capital W.
Okay.
And they're going to make, there are times that they make you use just how they structure the question, to type in capital W. The WebAssign is very case sensitive. Okay, you guys saw that with one of them had S in it the other day, and had used capital S. Just be careful with that. I call it U substitution because that's what you're going to use in calculus, and I want you to hear that terminology. And W substitution is just more to say. But you can use any variable you want, doesn't matter. So let's do this one. Is this one in a 2-to-1 relationship with the exponents? Yes. Okay. So we're going to do, we'll let U equal just the variable term of kind of that middle term. Okay. That would be kind of the B term in a quadratic, right? In order to do this, you need to make sure that you have your powers in descending order as well. Hi. All right, so we let U equal x to the third, right? So U squared, we're turn that into x cubed squared, which is a power to a power, so we multiply that, so we get x to the sixth. And that matches up there perfectly, right? And nothing is.
Yeah, I was about to say, Mr. Fay, you're
I don't-
crazy.
It's showing up on my screen. There we go. So U squared equals x cubed squared, which is equal to x to the sixth. So because that x to the sixth and that x to the sixth are the same, I know I've chosen the correct U. If they weren't, guys, what I would basically do is I would try something different. Okay? Chuck? Cool. So if you start off x to the 6 minus 26, x cubed minus 27, and you can see it, that's going to be x cubed minus 27 and x cubed plus 1. Is that what you're seeing? That's fine. Okay. Eventually, though, and that's a fine technique on this one. Eventually, this technique will have to be used at some point. So that's why, and I think it makes sense to show it now. When we get to trig, that's not going to be as easy to do, and we'll have to use U substitution. So I want to show that and learn that algebra now. I mean, you could use the quadratic formula here if you know what to set it equal to, okay? And things will pan out. So if I do this, u squared minus 26u minus 27 is equal to 0. What I was saying, if I was going to use the quadratic formula, I would set u equal to the opposite of b plus or minus all that garbage, right? But u would have been x cubed, right? So at the onset, if you didn't want to, if you couldn't see what Chuck was seeing and you couldn't factor it like our normal techniques allow us to, but you said, well, I'll use quadratic formula, that's fine. You just can't set the quadratic formula equal to x. You'd have to actually set it equal to x cubed. But I'm going to, like I said, I think getting it down to u, or in terms of u, is actually a better idea. Just because, and the thing is, because I know where we're going to go with this. I know the other types of algebra, other areas of algebra this is going to be useful in, that I think it's important to discuss. So then that's going to factor to u at minus 27 and u plus 1. And then I get u to be 27 and u to be negative 1. Okay, so u is what though? X to the third. So we're going to back substitute. Oop. And now how do I solve for x? Cube root. So I get x to be the cube root of 27. What's the cube root of 27? 3. Okay. What's the cube root of negative 1? Negative 1. So when you have an odd root, you can take the odd root of negative 1. And that's because of the multiplicity of an odd number of negatives gives you a negative, right? And those are my two solutions then. Okay? If we went back and we plugged things in, we would get it. Chuck at the beginning said he saw right away this is going to be x cubed minus 27, x cubed plus 1 equals 0. And he said, well, if I FOIL that, x cubed times x cubed, I add the exponents to get x to the 6th. 27 times x, negative 27 times x cubed, positive 1 times x cubed, add those together, negative 26 x cubed. Negative 27 times 1 gives me negative 27. That works. And does he then end up with x cubed equals 27 and x cubed equals negative 1? And that, by all means, is an efficient way that works. Now, what I would do, if Chuck says, I'm not going to learn this middle technique, and I'm not going to even worry about that because I can see this. Then the next question I'm going to ask is, Chuck, can you see that one? Okay? Because that's going to be a little bit harder. Okay? Now, it is the same idea. It's going to be, so Chuck had x to the third and x to the third because that needs to give me x to the 6th. So here it needs to be x to the 2/3 and x to the 2/3 of my first two terms, right? To get x to the 4/3. It's just a little bit more difficult, I think, with rational exponents to see that pattern. However, is this still quadratic? Is it still 3 terms, the last term being a constant, and is 2/3 still half of 4/3? Yes, it is. If you're not sure, take this one and double it. Do you get that one? And you do. Okay. So I'm going to let u equal x to the 2/3. Just let u be that thing right there. So u squared would be x to the 2/3 squared, which what do I do with a power to a power? Multiply them. So that gives me x to the 4/3. And that matches that. So now I'm going to do the substitution. U squared minus 5u plus 6 is equal to 0. What's that factor to?
U minus minus 2 and U minus 3.
So u equals 2 or u equals 3, right? But what was u?
X to the 2 thirds.
X to the 2/3. What are we always trying to solve for, though? X to the first, yeah. Okay. So how can I make X to the 2/3 through one step of algebra? How do I make X to the 2/3 X to the first? Multiply. Okay, so multiply by, now how, so I do need the reciprocal, but how am I going to multiply?
Is it when you make the square root thing?
I can't just say like multiply by 3/2. I can't do that. Okay? But you said multiply. I need this power to go to a 1. Can't I do this as a power to a power multiplication?
Yeah.
Will that give me 6/6?
Yeah.
Okay, so it's going to give me X to the first. But then I got to do the same thing to the right-hand side, right? And I'm going to write this as 2 raised to the 3/2. I'm going to come back in a moment after we do this right-hand side and talk about what 2 to the 3/2 really means. So once I figured that out, once I had to raise the left to the 3/2, I'm going to do the same thing over here. Raise this to the 3/2, raise that to the 3/2, and now I get X equal 3 raised to the 3/2. Well, remember what that means. The exponents mean I need to multiply my base by themselves that many times, right? Well, what does it mean to take something like 2 and multiply it by itself 1.5 times? What does that mean? That's hard to think about, right? What that means to us, guys, if you remember from Algebra 2, we might even talk about this a little bit in Algebra 1. If I have A raised to the m over n, that as a rational, we're talking about rational exponents, that is the same thing as taking the nth root of A to the m. Okay? The one that you've seen the most is like when this was just 1 over n. You took the nth root of just A to the first. So an example would be like A to the 1/2. You said, well, that's the square root of A, right? Okay? Well, if I have 2 to the 3/2, that's because of that. So the denominator is your root. So I'm going to take the square root of 2 raised to the 3rd. Well, that's the square root of 8, which is 2 root 2. And now because I introduced a radical, because I was taking the square root, it's plus or minus. So there's 2 answers for x right there. Okay? I do the same thing over here. It's going to be the square root of 3 cubed, which is plus or minus the square root of 27, which isn't that 3 root 3?
Yeah.
And there are 2 additional answers for x. Now there is a different place you can do that. Okay, right here when I had x to 2/3, and for some reason this generally becomes the way most students want to do this. They want to right here rewrite this as the square root of x cubed. And I think the reason they want to do it this way is because that it's more obvious to them that they can square this side and then square that side, right? And when we do that, we get x cubed is equal to 4, right? What happened here? What did I do here? 3/2. Oh, I messed up. This is a 3 and that's a 2, so that's a. Let's start. Let me erase this. My apologies. All right. So they write this as it was. All right, so just this red stuff. It was x to 2/3 equals 2, right? So what they want to do is rewrite this as the cube root of x squared is equal to 2. And then they realize I can cube that, so cube that. So that's going to give me x squared is equal to 8, right? And then they say, okay, square root, and that's where they get x equals plus or minus radical 8 or plus or minus 2 root 2. Okay? You can do it that, it's the same thing. It's just introducing that property in a different step. Yes?
You get to simplify like 2 root 2.
On test, I would be looking for that simplification, yes. And the reason for that is because remember, my main goal for you is to have the algebra skills that are going to set you up to be successful in calculus. And when you're in calculus, they're going to want you to simplify roots and do all that kind of stuff and just be consistent with that procedure. You want to scroll back over to it? Yeah. Hey!
Could we do one like number 7? We got like 3 minutes left. What's this one?
What do they both have in common? X and 8. Okay, so just read me the whole problem.
8x to the 5th minus 72x equals 0.
Okay, so they both have an 8 in them, right? They both have an x in them, right?
Yeah.
So it says x to the 4th minus, so 72 divided by 8 is 9.
9.
Okay, so this maybe isn't as obvious, but this is the difference of perfect squares. Because isn't x to the 4th the same thing as x squared squared? So then I can rewrite this as actually 8x. It'd be x squared minus 3, x squared plus 3. Now the way I would make sure that I've done this correctly, if I FOIL that, now they're conjugates, so O and I drop out. I don't need to multiply those. First times first is going to be x to the 4th. Last times last is going to be -9. So I have 8x equals 0. We have x squared minus 3 equals 0. And x squared equals, or x squared plus 3 equals 0. So this will give me 0. This will give me plus or minus root 3. This will give me plus or minus I root 3 when I do that one. And that'll be the case. So if x to the 4th was like, instead of x to the 4th, it was x to the 6th minus 9. I can rewrite that as x cubed squared minus 9. If it was x to the 8th, I can rewrite it as x to the 4th squared minus 9. And I can somehow transform that into a different first square. At this stage here, if you wanted to, you can rewrite right here. I can rewrite x squared as u, and now I got u squared minus 9. Might help me develop this a little bit quicker. U minus 3, u plus 3. Solve for x, solve for u, and those two things, and then back substitute that u. We got one more done in first period with some exponents that are negative and rational. They kind of look like where's that? So we did some of these. So we'll start with you guys on those tomorrow, and then we'll move into absolute value. Okay. That assignment is not due tomorrow. It's going to get pushed back. Okay. But don't fret if you don't see that get pushed back until tomorrow morning. Okay?
What about the one where it's like a fraction, but it's like x minus 9? We're going to go over those, because I've been asking every day, and you say yes, and we never do.
What question?
Is
What number?
14 maybe. I think that's where it started. What are we doing a lot of times, Dad?
Today's a meeting day.